Hi everyone and good morning. I am Ioanna Mitropoulou. I'm a postdoctoral researcher at ETH Zürich. And today I'm here to present the paper Chat with Pre-Demolition Audits, Knowledge Graph-Based Information Retrieval, which was co-authored by my colleague, Dr. Beril Önalan, who recently defended her PhD under the supervision of Catherine de Wolf. So, pre-demolition audits, what are they? Probably you already know them. They are a first in-depth documentation of building parts before major interventions. What's special about those audits is how early they are available. So they are available much earlier than other outlets that document reusable materials such as marketplaces. So they are detailed and timely, which could make them very valuable supports for early-stage reuse decisions. Now, ideally, from an audit, we would like to have a structured and accessible inventory. However, that's generally not the case. There are many challenges to getting there. And so some of the challenges are here. For example, the format is generally PDFs, so only human readable. There is considerable heterogeneity, so everyone has their own template. There is missing information, so while geometric attributes are generally documented, we usually don't have performance properties, for example, which are very important for use decision. And also, to access them, you need to have domain expertise and knowledge of how they're organized, which is usually not the case. So for the first three challenges, we address them in a journal paper that is at the moment being published, and here we will be confronted with the difficulty of access. So how can we democratize access to audits by developing an effective retrieval method that can retrieve information from natural language queries? Okay, so let's look what we have in pre-demolition audits. Usually they consist of two main parts. First, a tabular report, so a table, essentially, where information is structured in different categories, and second, a textual report, which is generally unstructured. So this is just text that describes important aspects of the audit. Now, information in those two documents is usually interlinked. So there is information in the text of the report that is very relevant to the entries of the table. And when it comes to retrieval, the main challenge that we are trying to address here is how to bring together such interlinked, structured and unstructured data. And the methods that we are using, unsurprisingly, is to employ a knowledge graph. The advantage of this approach is that it allows us to combine semantic retrieval using cosine similarity with graph-based retrieval that is based on relationships. And this is the workflow that we set up. So the user asks a question. This is the query. The query is given here to an, if I have a pointer, to an LLM router, which decomposes it into a series of steps. And then for each step, the router decides if it should be carried out with semantic search or with graph search. We use semantic search for finding conceptually similar entries using cosine similarity, and graph search for tasks such as counting entries, filtering them, or transversing relationships in the graph. And at the end of each step, the router also decides if relevant context from the report should also be added to the contexts. So let's see some examples of query decompositions. For example, for the question, what percentage of entries are marked as hazardous? This is decomposed into two graph search steps. First, counting all entries, and then counting all entries that are hazardous. And with this, we have enough context to accurately answer the question. If we ask that we need 30 square meters of exterior facade cladding in good condition, this is decomposed into a semantic and a graph search step. The semantic search is find exterior facade cladding entries, and then the graph search filter entries found in the previous step to those in good condition with at least 30 square meters available. So the combination of the information from those two steps is sufficient context for a good answer. So this is the proposed workflow, and then for validation, we compare our approach against a baseline Retrieval-Augmented Generation, which only uses semantic search. Now let's see how we build the knowledge graph. So we came up with this schema that consists of nodes that represent the main entities that we find in audits. So a project has a building which contains many entries which are categorized according to the uniformat schema. And then a project also has a report that consists of multiple text chunks. And it is here that all of the unstructured information is embedded into the knowledge graph. And this is an example of what a very small part of the graph looks like. So here we have our project in orange that contains a building, which has many entries in brown that are categorized according to uniformat. And then on the left, you see how all the textual report chunks are linked to that building. So we apply this to our case study. We have a case study in France that consists of 40 projects that describe 97 buildings. Most of these buildings are built between the 50s and the 80s, and they mostly consist, sorry you cannot see it, but it's mostly residential buildings. So, and I would like to thank Thibaut Meni and Azir for helping us gain access to those audits. It is not easy. Audits are kept as well-protected secrets, even for buildings that have been long demolished. Luckily in France, audits have been mandatory for a few years, so there is a large number of audits that are currently being produced, and this is why our case study is coming from France. So for this case study, the full graph looks like this, and it contains around 7,000 nodes and 13,000, a bit more than 13,000 relationships. Now, to evaluate our approach, we created a series of evaluation questions that fit into the following categories. So simple filtering, counting, then some more complex queries, queries also requiring report context, and then queries where the answer cannot be found in the dataset. And we ran this both for the baseline and for the proposed graph RAG. And we saw, of course, that the graph RAG performs better, especially for multi-stage queries that require counting and or linking different types of information. However, this comes at a significantly higher cost. So I don't know if it's big enough for you to see, but the tokens that are needed for the graph RAG can reach up to 3.5 times more than the baseline RAG. And this is due to how we have set up the process. So in the graph RAG process, we decompose the query into different subqueries. So of course, we make a lot more requests to the large language model. So for the future, we can think about perhaps developing a hybrid approach that combines a baseline RAG for simpler queries with a graph RAG for more complex queries. We can also, of course, think about a chatbot. So when we talk about chatting with a document, we want a chatbot that can maintain a continuous conversation. For this, we need memory of the discussion we've had up to this point. And perhaps for me, the most interesting extension would also be to start incorporating implicit relationships. So right now, the relationships in the graph were just explicitly mentioned relationships, but there's a lot of implicit connections that could also be captured and make retrieval significantly easier and more accurate. And of course, introducing explainability so that we don't just get an answer, but we also find out exactly how this answer was retrieved so that we can evaluate it. Yeah, this brings me to the end. Thank you very much for your attention.